Hello there, Mr. Sutton here with the IM3 Honors Chapter 1, Quiz 3 Review Solutions on Families and Transformations.
For this problem, I'm trying to figure out which function is represented here in the graph, what type of function. So this one at first glance kind of looks like an exponential sort of shape. Exponential, though, is a little bit different. With an exponential, you have a horizontal asymptote and you're going up forever. This one's going up forever, but there's no horizontal asymptote. There's actually a vertical asymptote right here. And you actually go down forever with this function. So when you have one of these undefined areas and a vertical asymptote, and you're going up and down forever, although one you're going steeply, the other not so steeply, that's the hallmark of a logarithmic function. So choice H on that one. Now, the more classical log function is kind of flipped over the origin here and looks kind of like this, if you can see what I'm doing with my cursor. Looks like a little r down here that goes down forever, but this is just another logarithmic that's been reflected a few times. For this problem, we're trying to figure out what type of function is represented by this graph. So we can go through and kind of cross a few of them off. Definitely not linear. It's not a parabola. It's not a snake. It doesn't have two branches with a bunch of asymptotes. Not a v, not a square root. Exponential it could be. We've got a horizontal asymptote right here on the x-axis, and we're going up forever. The normal exponential function kind of goes the other way, but this could just be an exponential that's been reflected. Definitely not logarithmic because there's no vertical asymptote. Definitely not sinusoidal. So we're going with exponential on this one, choice G. Trying to identify this function type by the graph, the key feature here is that we've got this distinctive V shape. So that's definitely an absolute value function. No other function has that kind of shape. So that's choice E. Trying to identify this function by the graph, we notice that this is a wavy repeating kind of graph. That means that this is going to have to be the sinusoidal graph. No other graph oscillates quite like that. So that's choice I. On this problem, I'm trying to identify what type of function this is. Now this is a parabola. It's a U shape. And we know that only quadratics or at least even-powered functions would make this kind of shape. Since we don't have a more general even-powered choice, we're going to go with the closest thing, which is quadratic, and that's choice B. As we're trying to identify the type of function for this graph, one thing we notice is that we have an endpoint right there, and that we're just going in one direction forever. You also might notice if we were to kind of flip this a little bit, we'd have kind of a distinctive R shape. That's the hallmark of the radical function or the square root function. But either way, the endpoint, this is the only graph that has an endpoint that only goes forever in one direction. So we're going to have to go with the square root on this one. That's choice F. For this graph, trying to identify it, we notice that there's kind of a snake sort of shape to this. Now, you might be misled a little bit in thinking that this kind of looks like a sinusoidal graph. The big difference here, although it looks like it's kind of going back and forth for a little bit, it eventually veers off into infinity in both the positive and negative directions. So this is telling us that this has to be a cube root kind of function, which is going to be choice C. As we're trying to identify this graph here, one thing we notice is that we have these two different branches, plus a vertical and a horizontal asymptote. So that could only be a rational function then, which is choice D. On this problem, we're trying to figure out if this function is even, odd, or neither. So the quick way of telling if you have a polynomial like this one is to just look at the exponents and see if they're all even, constants counting as even. In this case, they are, so that would tell us this is going to be an even function. If all the exponents were odd, it would be an odd function. If it was a mix, it would be neither. Now, the longer, more official, more rigorous way of telling is to plug in negative x for all the x's and see if we get the same thing we started with. If f of negative x equals f of x, that would tell us that we have an even function. So let's go ahead and do that just to show you. So we have 3 and then negative x to the 6th plus negative x squared plus 9. And then we'll just see if this comes out to the same thing we started with. So this is an equals question mark with the original here. Now let's actually go through and see if we get what we started with. Negative x to the 6th power, Well, that's going to be an even number of negatives multiplied together, so that's going to be a positive. So 3x to the sixth, positive 3x to the sixth. Same deal kind of over here with this even power. This is positive x squared, and that plus 9 is still there. And looking carefully, we've got positive 3x to the sixth, positive x squared, 9. That's exactly what we started with. So this proves that we have an even function here. For this problem, we're trying to figure out if we have an even, odd, or neither kind of function right here. The quick way of doing this one is to notice that we have all odd exponents in a polynomial, which automatically means we have an odd function. But we don't have to do the quick way. We can do the more rigorous test here, which involves plugging negative x in for all the x's and seeing what happens. So first we'll test to see if it's an even function, since that's a quicker test. If we plug negative x in for all the x's, so 4 negative x cubed plus 2 times negative x, we want to see if that gives us what we started with. If f of negative x equals just plain old f of x. So going through here, a negative raised to an odd power gives me a negative. So this is negative 4x cubed. This, of course, will be negative 2x. And taking a look at this versus what we started with, we see that these are not the same thing. One of them is the other thing with the opposite signs. So these do not equal each other, which means this is not an even function. But it still might be an odd function, or it might be neither. We don't know until we test. So the next test for testing if it's an odd function is going to start the same way. We're still going to plug in negative x for all the x's. But now we're trying to figure out if doing that gives me the exact opposite of f of x, of what I started with. If f of negative x equals negative f of x. Algebraically, we're asking, does this stuff give me what I would have gotten if I took the original and multiplied everything by negative 1? So going through again, we still have negative 4x cubed and negative 2x on the left side. On the right side, distributing this negative, we have negative 4x cubed and negative 2x. These two are an exact match, so that tells us that this is indeed an odd function. Now, if this test had failed, then we would have concluded that we had neither kind of function, but we do end up with an odd one here. To graph this absolute value function, I'm going to start by writing down the points of the parent function that I always use, negative 1, 1, 0, 0, and 1, 1, in a nice little table there. And next, I'm going to figure out what kind of transformations are going on. This negative 2 outside the function is telling me that I've got a vertical reflection from that negative and also a vertical stretch with that 2. So basically multiplying the y values by negative 2. The minus 2 inside is telling me that I'm shifting to the right 2, opposite of what we would expect because it's inside the function. So vertical reflection and stretch and right shift of 2. Let's go ahead and put that in another table now where I transform all these individual points. So for the x's, because I'm shifting right 2, that means I have to add 2 to the x's. For the y's, again, we're multiplying those by negative 2. Let me do the x's first. So we've got negative 1 plus 2 is 1, 0 plus 2 is 2, and 1 plus 2 is 3. For the y's, multiplying each of these y values by negative 2, I have 1 times negative 2 is negative 2. Then we have 0 and negative 2 again. Graphing these new 3 points out now, we've got 1 comma negative 2, that's down here, 2 comma 0 is right here, and 3 comma negative 2 right there. And then we'll just draw the V going through those. And it looks like an absolute value shape that has indeed been reflected and stretched a little bit and also shifted to the right by 2. To graph this square root function, I'll start with my 3 square root points that I always use and the parent graph table here. So I've got 0, 0, 1, 1, and 4 comma 2 that I'm putting in this table. And just taking a look at the function and to see what's going on, the plus 3 inside means I'm shifting left 3, opposite of what you'd expect. The plus 1 outside means I'm shifting up by 1. So to put that in a table here and transform these points, if I'm going left 3, I have to subtract 3 from the x. Up 1 means I'm adding 1 to the y values. So x minus 3, changing all these x values, 0 minus 3 is negative 3, 1 minus 3 is negative 2, and 4 minus 3 is 1. Adding 1 to all the y values now, we have 1, 2, and 3. Now we'll just graph these on our coordinate plane here. Negative 3, 1 is right there. Negative 2, 2 is right there. And 1, 3 is up here. And the end point, because this is a square root function, so we have to nail the end point here. 0, 0 was the old end point. That transformed into negative 3, 1, which is right here. So we're going to start here and just go in one direction through those points. To graph this square root function, let me start with my parent table with the points 0, 0, 1, 1, and 4, 2. And let me look at the transformations that are happening. So inside, we're multiplying by negative 2. That means since it's inside, it's going to be horizontally affecting our graph. This negative gives us a horizontal reflection, and the times 2 means we're actually dividing the x values by 2, or shrinking this thing horizontally. The minus 4 outside means we're shifting down by 4. So to recap, reflect and shrink horizontally, multiply x by negative 1/2 when all is said and done because of that negative there. And we're going to shift down by 4. Putting all that in a table, my x values, again, getting multiplied by negative 1/2. So negative 1/2 x is what I'm going to write up here just to remind myself what I'm doing to all the old x values. And if I'm shifting down 4, that means my y values have to be subtracted by 4. All right, let's go ahead now and apply those changes. So negative 1/2 times all the x values. 0 times that still gives me 0. Negative 1/2 times 1 is negative 1/2, or you could call it negative 0.5. Negative 1/2 times 4 is negative 2. Now y minus 4 for all of these. 0 minus 4 is negative 4. 1 minus 4 is negative 3. And 2 minus 4 is negative 2. Let's go back and graph those 3 points. 0, negative 4 is down here. Then we have negative 0.5, negative 3. That's right about there. And negative 2 right here. Now the end point, the starting point for this square root function was originally 0, 0. That has turned into 0, 4 with our transformations. So that's this point right here where we're starting and just going through the other points in only one direction.